Hello and welcome to another video. In this video we're going to be working on Knight Dealer, and in this problem you have a chess knight which has a unique movement, so it makes like an L shape, where it can move two squares in one direction and then one square in another, and the two directions have to be opposite, so it can go like two squares horizontally and one vertically, or two squares vertically and one horizontally. And so they have a diagram here, and we have a chess knight and a phone pad, and the knight can only stand on a numeric cell, or blue cell. Given an integer n, return how many distinct phone numbers of length n we can dial, and we can place it on any cell initially, and then we should perform n-1 jumps. All jumps should be valid jumps, and if the answer is too large, return this. So let's go through the first example. In the first example, we have n equals 1. So for n equals 1, that just counts placing the knight, so we can just place the knight on any one of these blue squares, and that will give us 10 different cells. In the second example, we can place the knight, and then we can move it. So this is actually going to be very useful, and I'll talk about it in a little bit. And the third example, there's some big number, and it turns a big number. So essentially what we want to do first, and also the constraints are 5,000, so you can have something like an n-squared solution would pass, or something like that. So definitely dp would work here. And we're also asking for a count, and usually when you're asking for a huge count, dp is one of the things you look for first, because dp is pretty good at getting like combinations. You just have like valid combination, things like that. So what you want to look for first is, given a square, what squares can the knight go to? So for example, if we're on 1, what squares can we go to? Because it's going to be very hard to like figure out all the movements, but we can just map every square to two squares that it can go to, right? So like 1 can only go here and here. So 1 can go to 6 and 8. 2 can go to 9 and 7. 3 can go to 8 and 4. 4 can go here. Can go here. It can also go here, so it can go to 3 squares. 5 can't go to anything. So with 5, no matter where you go, you're never going to be in bounds. So 5 can't go to anything. 6 can go to this square, and this square. 7 can go to this square and this square, I believe. I think that's all of it. And then 8 can go to this square, and 9 can go to this square and this square. And they actually provide all of this for us here. So when n equals 2, these are all the like where you can go from every square. So from 0, you can go to like 4 and 6. From 1, you can go to 6 and 8. From 2, you can go to these, and so on. So they actually provide us the mapping. And so what we're going to have first is we're going to just make a dictionary of a starting number. So we'll write this down. So we're going to have a dictionary of, and the key will be the starting number, and the value will be array of numbers we can go to. And now we can use this easily in our DP. So in our DP, let's just make some conditions for DP, and let's show what we're going to do. So essentially, first we need some kind of state. So the state we're actually going to have, all we need, so let's write this down. For the state, all we need is two things. One, we need the actual like index, obviously, right? Like how big our number is. There's no way around that. And then the other one is we just need to know like what was the last digit that we had. So last digit that we had. And then from there, we can just look where to move, right? So this is one way of doing it for a memorization solution. So for example, let's just look through some examples. So let's say we started at digit 0. So we'll say like, okay, we're at index 1. And then where can we go? Our last digit is 0 as well, right? So we're at index 1, like n equals 1 here. Our last digit was 0. Where can we go from 0? Well, we can go to 4 and 6. So we would just recurse into two states, right, where the index would be 2 and 4, and it would also be 2 and 6. And we can just add all these up. So from every number, we can write this down. Let's actually wait for that in a second. So let's actually do the base case first. The base case is pretty straightforward. The base case is index equals n. Yeah. So if index equals n, then we want to return 1, right? Because we are at some valid thing, and there's only one thing there. And we're never going to have like a case where it doesn't work. But essentially for the recursive case, all we have to do is loop through every number we can go to and add them up, right? This is like a standard, you can traverse in a bunch of directions. How many different paths can you make? It's just going to be the sum of going in every single direction, right? So for example, let's go back to our example. Let's say our number was 0. So our phone number was 0 and our n was 1 here, like as a starting index. And so here, where can we traverse to from 0? We can traverse to 0, or we can traverse to 4 and 6, right? From 0, you can go to 4 and 6, and also looking at the picture, from 0, you can go to 4 and 6, and those are the only numbers. And we're just going to use our mapping to make it really clean code. So then we'll say, okay, so if we're here, we just need dp of, and then what's the last number now? So if we go to 4, dp will be 4, and the actual length of the number will be 2, plus dp of 6, 2. And now let's say we were at this starting thing, n is 2, so now that we've reached the number we want, this will just return 1 for each of them. And that makes sense, right? Because we can get two numbers. We can get 0, 4, and 0, 6. So you just basically keep doing this, and you keep recursing to every single number you can go. And when you're on a 5, it will just automatically return 0. So let's say we were on like 3, or whatever. What number can you get to 5 from? You actually can't get to a 5 from any of them, but let's say you started on the 5. So if you started on the 5 and you try to go to more places, it would just give you 0 because there are no numbers you can go to. So when we add up all the numbers we can go to, there are no numbers we can go to, so we just return 0. And that part is pretty straightforward. So yeah, and that's basically it. So literally just have the state of the index, last digit we had. I think there was a very similar problem on LeetCode actually, where it's like the length of like, or all the strings you can make where you can only go from like one letter to some other letters. It's basically the same thing. You just create a mapping, and then when you create a mapping, you just recurse and add them up. And it's like a pretty standard DP problem where it's just like an add all paths. So let's code that up, and then let's do some optimizations. So let's code this up now that we know exactly what to do. So first thing we're going to do is we're going to create the mapping. The mapping actually made beforehand just so it's easy. So it's basically what our number is and all the numbers we can go to. Once we have that, we'll have the mod variable. So that's going to be 10 to the 9th plus 7. We'll also have a cache, just a normal memoization. And we'll have a result. So result equals 0 and cache equals 0. We can actually make the result equals 0 farther down. So our cache needs to just be a dictionary. And we're going to have our DP function. So it's going to take an index and the end, which is like the last number we were at, right? So if index equals n, that means our number is long enough, so we just need to return 1 because our number is long enough. Otherwise, also if this tuple is in the cache, so if index end in cache, then we can just return that. Cache index end. And finally, now we're going to add up all of our different places we can go to. So we'll just set up and result equal to 0, and we'll say for move in moves end, right? So whatever character we're at, let's say we're at a 0, these are the moves we can go to. So for every single move, let's get the DP of it. So we'll say result equals result plus DP of, so what's the end going to be? It's going to be index plus 1. And the new end value is just going to be where we move to, so it's going to be move. And we're also going to mod it by mod to keep the result small. So we're going to mod it by mod, and then we will cache it at the end, right? So we went through all the moves, we've added them all to the result. Now let's cache it. So index end equals result. And finally, let's return result. And so this DP function handles starting at one number, right? So we know that we can start at every single number from the problem. So we're basically going to have to run this function starting at every single number to get us every single number we can make. So what we need to do is we need to just loop through this, and we're going to make a total result variable. So we'll say for I in range 10, right? We need to start at every single number 0 to 9 and see what's the total of the numbers we can make here. So result equals result plus DP. And the original string length is 1, right? Because we're just going to give it an I. So like we'll give it 0, let's say. So if we only want a 1-digit number, we'll basically be done. So this is going to be 1. This is going to be whatever number is in here. It's going to go 0 through 9. And we'll mod it by mod. And finally, we will return result. So pretty straightforward standard memoization problem where you're just counting up all your different paths. And let's take a look. So we do have a effective solution here. Actually, let's submit it. Sorry. Well, actually, I think we did submit it already, right? Yeah. Yeah. So we did submit it. Let's see okay. So here we go. So our runtime is pretty good. Our space is okay. So we can improve it. And I will briefly do this. I'm not going to go in super detail, and I'll link the video on space optimized bottom up. because this is going to take a while to explain. But essentially, we can look at when in our recursive state, we are increasing the index by 1 every time. So we can optimize this to get rid of this dimension, right? Because if we're only recursing to the next index, we don't need to store the entire number. We just need the previous one. So because this dimension only increases by 1, we can get rid of this dimension, and then we can have a basically O of 1 solution. So let's do that now. So let's get rid of all of this. We'll just comment it out, and then I'll briefly explain how to do this. So essentially what we're going to do is we're just going to have a DP array, and it's going to start with this. And this is basically means for a number of length 1, we're going to have every single number 0 to 9, right? So if we're going to have every single number 0 to 9, that means we'll have an array length 10, and the index will represent the last digit of the number, right? So in the beginning, we're just going to have like, there's one number of 0, there's one number of 1, one number of 2, one number of 3, one number of 4, and so on. And that's how the initial 1 digit starts. And now basically we have to loop through this thing n-1 times to actually figure out like how many more digits do we need. And so the reason we need to loop it, or we're going to loop to like this, so we're going to say for, we don't need this value in range n-1, because let's say n was 1. If n was 1, we wouldn't want this to loop at all. So now this would be 0, which is fine. If n was 2, we'd want it to loop 1 time, right? Because if n is 1, we already have our array of numbers. Like we already have our array of numbers. And this array, like I said, represents the total number of numbers that end with each digit from 0 to 9. So we're going to loop this amount. And we're basically going to, in the space optimized bottom-up video, like I talked about, we're going to create a new array every time. It's going to be called new moves, and it's just going to be initialized to 0 times 10. And then what we need to do is we need to go through every number in the original array, and that number is going to have some count of numbers that end with that. And we basically have to say, okay, let's take the count of numbers that end with that, see where we can go. And so let's say we had like, let's say we were on some digit in n, like 5, and we were on some number, like we were on some like number that ended with 2, and we had like 10 of them. So then we would say, okay, if there's 10 numbers that end with 2, that means we can go to 7, and there's going to be 10 numbers that end with 7, and we can also go to 9, and there's going to be 10 numbers that end with 9. So basically, for whatever that is, we have to go to every single move, and in that move, we have to add what our previous number was. So kind of confusing, but hopefully that makes sense. And like I said, if it doesn't, watch the space optimized bottom-up video to explain it a little bit better. Okay, so what we need to do is we need to loop through all of our numbers in our original DP. So for I in range 10. And then also for every single original number, we need to see like where can we move to from that number. So the way we do that is for move in moves I, we're basically going to be adding here to the new array. So we'll say new moves, move, right? So wherever we can go to from the original number to the new number, we need to add what that old number was. And then finally, at the very end, for all the space optimized bottom up, you make a new array. And then at the very end, you make your old array equal to the new array. So we'll just say dp equals new moves. But if you are just able to get a memoization solution, that's totally fine. Like that's still pretty good. So it's not super important to understand this one. And then finally, so now our DP is going to contain the number of numbers that end with each digit that are length n. So let's say n is 10. It's going to give you like, okay, what are the number of 10 length numbers that end with 0? What are the number of 10 length numbers that end with 1, and so on. So basically, to get all of the numbers total, we have to sum up this array. Or not this moves, but our DP array. So we just have to return sum of DP mod. And that should give us every single number possible. So we can try to run that. There we go. And let's actually zoom out of this. So there we go. So this one's a lot more efficient. You can see this one is like 16, and the other one I think was like 45, yeah, 42, 43. So it's a lot faster because we're using tabulation. And in theory, it shouldn't be faster, but because we are using like tabulation and no caching, and we're storing a lot less, it's going to be faster. So let's talk about the time and space for each of these, just to get some practice in there. So for this one, so if we take a look, there are two dimensions here, right? The dimension is index and end. And so for index, that's going to be basically n. And end can only be like 10 numbers, right? So that's going to be negligible. That's going to be O of n total. And also we're running this 10 times, but that's also negligible. So it would be like 100n, but that's basically negligible. So time would be O of n here. Also in move, each thing can only move to like 2 or 3 moves. So this for loop is basically O of 1, this end is basically O of 1, and this loop is O of 1 as well. So that's that. And for the space, it's also O of n, because like I said, there's only like 10 numbers that you can end with, so that's negligible. Now let's look at this one. So the time is going to be O of n because we are looping through like all 1 to n. So that's still O of n, but the rest of it is going to be negligible, right? So this is negligible because it's only 10. This is negligible because it's only like 3. So this whole thing is negligible. Also now our array, the nice thing about this one is our array is only 10 elements every time. So because our array is 10 elements every time, our DP is 10 elements, and our new DP is 10 elements, we have O of 1 space. So we've gotten rid of the index dimension. And I think, yeah, that's going to be all for this one. So if you do want practice doing this space optimized bottom up, definitely I'll link the other video. You can practice it. I will say going from memoization to space optimized bottom up is probably like just as long as getting the memoization. So it's kind of like, is it worth it for you? You know? And yeah, that's going to be all for this one. So if you did like it, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.